Hi, I'm James Miley, and sometimes when we're modelling protoplanetary disks, we adopt values from their later stages that we're currently observing, but that forgets that, especially in younger stages, these stars are evolving very quickly, and that these changes are going to have effects on the disks they host as well. So my video poster is on the impact of pre-main sequence stellar evolution on the midplanes of protoplanetary disks. A big thank you to all my collaborators whose names are at the bottom. So I'm interested in giant exoplanets, and particularly those on wide orbits, such as the ones I've circled here. Usually we find them through direct imaging. And I'm also interested in intermediate mass stars because they are the ones that host massive, long-lived and radially extended disks conducive to forming these giant planets on wide orbits. And when we observe them with high-resolution ALMA observations, we see lots of substructures that suggest the presence of giant planets in the outer disks. And even in radial velocity surveys, the giant planet detection rate peaks at around the stellar mass range of intermediate mass stars, just under 2 solar masses. And the other interesting thing about intermediate mass stars is that they evolve slightly differently to the low and high mass stars. So we can see here in this circle, they decrease in luminosity quite rapidly like low mass stars at first, but can then increase again at later stages and change a lot in temperature like the high mass stars do. And it's this behavior I wanted to have a look at and to see what the effect was on the temperature of the protoplanetary disk that these stars are hosting, because it's the temperature that sets the composition in the disk, the building blocks for planet formation. And it does this in the first instance by setting the position of snow lines radially. And these segregate the disk composition of both the gas and the solid phase, as was shown by modelling here by Oberg et al. In 2011. H2O, CO2 and CO were all major parts of this. So what is the temporal dependence of this picture, and can we begin to link the planets that form in these disks to the conditions they came from? Can we guess when and where a planet may have formed based on its C to O ratio? So to do this, I combined a number of types of different modelling. Maser modelling of stellar luminosity evolution in the pre-main sequence. Then we calculated reliable, self-sufficient, self-consistent temperature profiles using MCEMAX. And the chemical model of Oberg et al. Wrapped into a mid-plane model that includes things like radial drift, which are important for moving volatiles from the outer disk to the inner regions. And this is the first set of results we got. This is from the radiative transfer modelling. So on the left-hand side, we've got some temperature profiles. The disks around low mass stars we see get cooler over time because the luminosity of their central star is decreasing. But if the mass of the disk stays the same, which is a key assumption of ours, the disks around intermediate mass stars get cooler but then heat up at later times. And we can see the effect this has on the CO snowline on the right hand side, where for the disks around low mass stars, gas phase CO must be concentrated in the very inner regions of the disk, whereas in the intermediate mass stars it can be for a great portion of this disk, nearly all of it. So to apply this, we can look at a system that's already formed for giant planets and for which we have some fairly good C to O measurements as well for some of them. And this is HR8799. I'm particularly interested in planet B because it's on a very wide orbit and has a very high C to O ratio. It's very rich in carbon, so it must have accreted quite a lot of carbon-rich gas. So this is my version of the Oberg et al. C to O plot. The solid line on the top plots the gas phase C to O ratio, and it's plotted up to the CO snow line. So there's no more gas phase, carbon or oxygen outside of that. On the bottom, the dotted line is the solid phase C to O ratio, and that peak that is growing, you'll see when this restarts, builds up at the CO snow line as material drifts inwards. So there's a build-up of solids and there's a gas plume on the inside. So HR8799 is our very B is our very carbon-rich planet on this wide orbit, and it must have formed through the accretion of quite a lot of gas very quickly, and it must have taken quite a lot of carbon because it's got this very high carbon to oxygen ratio. So we'll see when this restarts, because this is a 1.5 solar mass star, the CO snow line moves in quite quickly and it doesn't move back out that far. But what we do see is that by about this point, about 1 million years, the CO snow line seems to move inwards of the position of HR8799b, according to our radiative transfer models and for the disk mass we've assumed here. So that means planet B must have accreted the vast majority of its carbon and oxygen before this point. So at the moment, after this point, there's just hydrogen, right? There's not much to bring that C to O ratio up to the really high value. HR8799c is slightly more complicated. Must have accreted quite a lot of planetesimals to get that lower C to O ratio. So thank you very much for checking out my video poster. Please do get in touch.